And I also wanted to talk about what, if we're going to compare different molecules, which ones would have larger London forces. So we've got our electrons. Here's essentially the size of our move over a little bit. Here's our molecule. Like, here's the volume of the molecules taking up. And we've got these electrons. Okay, right there, positive charge. So the electrons are like, ooh, positive charge. Attracted over here. Of course, they're distributed around, so there's some over here too. But we have a little bit more electrons on this side being attracted to the positive charge. And what that means is because molecules have nuclei that have positive charges in them, and now this side of the molecule has more of the electrons, it means there are fewer electrons on this side. Electrons are negatively charged. There are fewer electrons on this side. And so this side of the molecules now, for that instant, has a slight negative charge. This side, where the electrons were attracted to a positive charge that's over there, so that's causing this side of the molecule to be slightly more negatively charged in that instant. Okay, things are always moving though, right? Imagine that positive charge from another molecule nearby. Say that's moving. Everything's moving. Everything's moving. Unless we're at absolute zero, everything's moving. Okay, so let's say that positive charge then moves up there. And then it's like, ooh, now the electrons are going to be attracted there, and they're not attracted there. So there's this constant movement of these electrons, and there are these constant instants, moments in time, picoseconds, femtoseconds, where this molecule is a slight polar, meaning it's imbalanced in the positive charge and the negative charge on this molecule. We're going to have these instants where there's a little bit more electrons on this side now. Now there's a little bit more electrons up here. Now there's down here, constantly moving around the molecule. This is the origin of London forces. London forces are these attractive forces by virtue of electrons being polarized is the term. This polarizability is the amount by which the electrons can move around in a molecule. Then we get nearby molecules reacting to that. If there's a little bit more of a negative charge over here, it's going to affect a nearby molecule. If there's a little bit more electrons over here, it's going to affect that molecule. Likewise, this molecule that we're pretending to be, we are influenced by nearby molecules and any charges that they have. So there's our London dispersion forces, literally hand-waving description of what's going on. Okay. So the cool thing about London dispersion forces, and if I go back to one of these, I don't even know. Is this the one? Whoa, that was lucky. Which one is that? Okay. So the cool thing about London dispersion forces is that they work for any kind of molecule, whether they're polar or not, whether they're nonpolar. Okay. So so that it works for every molecule, but I want to point out here that these are the only intermolecular force. That's what IMF stands for. Intermolecular forces. Okay. That's relevant to non-polar molecules. All right. Non-polar molecules. Okay. Can we think of some non-polar molecules? Chemists out there. What non-polar molecules are there? We could first think of some non-polar elements. Are there any elements that exist by themselves? Like perhaps one of these, one of our noble gases, say xenon, floating around? Okay, xenon is a monatomic gas at room temperature. Monatomic, just one atom, neutral atom floating around. It's got a bunch of electrons. How many electrons does it have? Oh, if only we had a periodic table. Oh, that's right, we do. Okay, so xenon, if we check out xenon, 54, you gonna focus? Come on, you can focus, you can do it. So 54 protons, that means it's got 54 electrons. Right there, our atomic number. Why isn't it focusing? What if I brought it in really close? I wonder if it can do that. Ooh, yes, I should have done that. Okay, so 54 electrons can be flowing around our xenon atom. Okay, what else? Ooh, I think I have. Here's one. Here's a molecule. This would be the equivalent of sulfur. The colors don't match, but here's the structure of sulfur hexafluoride. So if each one of these white balls here, if these are fluorine atoms, we're used to, really the convention is the white ones are the hydrogens, but let's just say these are fluorines, okay? And then the central atom is a sulfur, okay? This is a symmetrical molecule. It is symmetrical in its geometry. This is octahedral. And it is symmetrical in terms of all of the peripheral all the peripheral atoms are the same. And we've got something like this with this symmetrical molecule. We're also going to get a nonpolar type of molecule. What else? We have carbon dioxide. We've talked about that before. Linear and symmetrical. And so the electronegativity of the oxygens pulling in equal strength away from the carbon, equal in opposite directions. That ends up with it being nonpolar. But I gotta say, a quintessential, very typical nonpolar molecule are any kind of hydrocarbons. Okay, so this is an alkane that I have here. These are carbon atoms, and this is a carbon chain. So we've got 1, 2, 3, 4, 5, 6, 7. All right. This is heptane. Okay, but I'm just going to put here, just in general, hydrocarbons. All right, so hydrocarbons, anything that's just hydrogen and carbon, because they have very similar electronegativities. And so essentially any kind of dipole there is cancels out. All right, and we see that with something like this heptane that we've got here. So, all right, so there's our London forces. There's kind of our overview of what they are and what kind of molecules we see them in. All right, and I also wanted to talk about what, if we're going to compare different molecules, which ones would have larger London forces than other ones. Okay, so we can compare strength of London forces between different molecules. Okay, so I really want to do that with some alkanes. All right, so let me move some of this stuff out of the way. I want it to be kind of tabula rasa. Okay, so we can kind of see what's going on. And I'm going to let's do some building together. All right. Let's get our molecular model kit. Mega molecules. This is my favorite one. Oh, here we've got how many? I might make this one smaller so that we can let's make it 5. Okay. 1, 2, 3, 4, 5. Let's look at this one. Okay. And first thing we're going to do is we're going to compare these two. Okay, but I do want to get some other ones handy, so I'll get these out and then make some room. Okay. So let's look at these two molecules. These are two, as we said, hydrocarbons are nonpolar. All right. And these are two hydrocarbons. These are carbons. This one has 5 carbons. This one has 2. All right. So the name of this is ethyl. I'm sorry. Well, it's an ethyl group, ethane. And this is pentane. And we are assuming all the hydrogens are there. Like, see where this comes out? That's a little hydrogen is bonded there, hydrogen bonded there, and all of that. Okay. So we're looking at, if we wanted to write out the formulas of these, we're looking at C2H6 versus this one is C5. Oh, and actually, if I don't know how many of you out there have done organic chemistry, but the rule of thumb when you're looking at alkanes is that the formula is always going to be however many carbons you have, you double it and you add 2 to get however many hydrogens there are. So that's always true for the single bonded alkanes. If you haven't had organic yet, that's totally fine. You don't need to know that. I just wanted to point that out for those of you who did. Okay, so let's compare these and which one is going to have the stronger London forces. All right. And so we think about what's going on, our whole description of the beehive and the electrons that are moving around, that are constantly moving around in each of these molecules, and how they can be affected by nearby molecules. And as they're flowing around, that sometimes you can have slightly more electron density on this side than there is over here, and slightly more electron density here than there is here. And then the next instant, that's going to change. Okay. And so what that means is when we look at a larger molecule like this pentane, that means that there are more electrons. That means that there are more electrons that are moving around. That means we have like a larger beehive, a larger swarm of bees that can move around and create in any instant some kind of slight dipole that's there. This ethane molecule, this is just fine by its own right, okay? Lovely little molecule. It just does not have as many electrons. And so in terms of the electrons in this molecule being able to swarm around, yes, they can do it. But in terms of getting more electron density on one end over here than on this end, it's just going to be a smaller chance just by virtue of there being fewer electrons that are moving around. So overall, what we look for when we are comparing two different molecules, the larger molecule. And you can look at larger simply looking at the molecular mass of it. Okay, that's one way to do it. Between two similar kinds of molecules. These are both alkanes. Okay, so this one is larger. In other words, more electrons. Okay. So this one is going to have stronger London forces. And I'm using red. I think you can see the red. Okay. Larger, more electrons, larger London forces.